Hello everyone, welcome back to my channel, and in this video we'll be solving this problem from the book Pathfinder, and this is from the MCQ section of the chapter Impulse and Momentum. So we are going to be solving this problem with just one equation. So let's see what the problem is actually asking us. So we have a large block A that consists of a frictionless slope of height 40 centimeter, which smoothly merges into a horizontal flat portion. The block rests on a frictionless horizontal floor. When a small block B of mass 1 kg is released on the top of the slope, it slides down the slope and then it stops after sliding a distance of 1 meter on the horizontal portion of the top of block A. So we have to find the coefficient of friction. So basically this curved path of block A is smooth and this horizontal path is actually rough, which means there is some friction. So as this block will be sliding down, the decrease in its potential energy will be eaten up by kinetic friction basically. And it is also given that the block slides a distance of 1 meter relative to this block A. So do give this problem a try for 3 to 4 minutes and then come back later for the solution. So before we get into the question, we have to discuss a small concept. So let's take two blocks, M1 and M2. And the ground here is actually frictionless, but the top of plank M2 has some friction. And let's say the friction coefficient here is mu. Now, let's say we give the mass M1 some velocity V, right? So obviously friction will act on M1 in the backward direction, and kinetic friction will act on the mass M2 in the forward direction. So the M2 will have a forward acceleration, M1 will be decelerated, and after some time what will happen is both the block and the plank will move with the same velocity and the friction will be static in nature. Now let's say the mass M2 moved by a distance of x2 and the mass M1 got displaced by a distance of x1 in the process. If you look at the mass M1, it will have the force of kinetic friction acting in the backward direction, right? So the work done by kinetic friction on the block M1 is going to be minus Fk times x1, right? And it is minus because the force and the displacement are in the opposite direction. And similarly, the work done by kinetic friction on mass M2 is going to be Fk multiplied by x2, right? And the magnitude of friction will be same since it's action-reaction pair. And its displacement, the displacement of mass M2 is going to be x2. So the net work done, and if I take a minus sign out of it and add both of these, it's going to be Fk times x1 minus x2. And if you observe something, x1 minus x2 is simply the relative displacement of this mass on the plank, right? So from here, we have a very important fact coming out of it, that the work done by kinetic friction is actually frame independent. But it only depends on the relative displacement that one body covers with respect to the other body. Okay, so we are going to be using this fact in this particular problem. So now as the block B comes downwards, a normal force acts on this block A and it will move towards the left. So when the block B will reach the bottom, the work that kinetic friction does on the system is simply the force times the relative displacement of block B on A, right? Which is given to be 1 meter. So if we just use the work energy theorem, the entire potential energy of the system, which was mgh, gets eaten up by the work done by kinetic friction, which is simply the magnitude of kinetic friction multiplied by the relative displacement, which is 1 meter, right? Now Fk is simply going to be the coefficient of kinetic friction times the normal reaction. And normal reaction at this point is simply going to be the mg. So this is going to be mu mg, and from here, we'll get the value of mu as h, which is actually 0.4. So that was it for this video, guys. If you have any doubts, you can comment down below. And do like and subscribe to the channel if you enjoyed the video. And thanks for watching, guys.